Well, welcome to the next talk this afternoon for EHSM, the second edition. Next up is Yann Sionneau. He's part of MLab's community, which is this really cool community that works with FPGAs. That's a way of doing really intense electronics, including Milkymist, which was developed by Sébastien, the main organizer of EHSM. Yann is developing open source designs for making it possible for open source designs with FPGAs. And he's going to talk about today open source CPU and adding an MMU to it for NetBSD kernel. There's a lot of acronyms for you, but he's going to talk about it and make it so you actually understand all that if you don't already, and if you do, he'll get into more about it. So, and hopefully at the end, there'll be a demo. Yeah, so let's hope that works. Take it away, Yann.
Hello, can everyone hear me? Okay. First, thanks for attending this talk, and thanks to Sébastien and the EHSM organizing staff for inviting me here. Today I will be talking about porting NetBSD on an open source CPU, which is called LatticeMico32. Okay, first bug, the remote is not working. Okay, that's working too fast. A bit about me. So Yann Sionneau, I'm an embedded software developer. I'm working for a French company called Sequence Communication, making LTE and WiMAX chips. I'm a contributor to the MLabs, founded by Sébastien, and you can find me on Twitter. So I'm going to talk about how to run NetBSD, which is a modern operating system, and HBSD. HBSD is basically a fork of NetBSD, so every time I'm going to talk about NetBSD, it applies as well for HBSD. And those will run on the Milkymist One. So in the first part, I will talk about a bit of hardware, which is the MMU. MMU stands for Memory Management Unit. I will explain what it is and how it works. And then a bit of software. I will explain how to modify the source code of NetBSD to make it run on this new CPU. CPU is a processor. So, Milkymist One, what is it? It's an electronic device aimed at generating artistic video performance during parties or concerts. It works a bit like this. So you can basically capture a live performer and project it against a wall or against a screen and apply video effects like rotations, zoom in, zoom out, blurring, etc. And you can control as well lights and sound. And everything in the box can be synchronized with the music. So it's generating effects like this. For instance, those are screen captures of the Milkymist One. So the main component of this electronic device is an FPGA. That's a chip, as you can see. So what is an FPGA? It's a chip. It's an array of logic blocks. It's good that in the previous talks we talked a bit about Lego bricks, because in fact it's a bit like playing with Lego bricks, because you can configure those many logic blocks like you want. It's like choosing a Lego brick, and then you can configure all those straight lines, which are programmable switch matrix, and then it means that you can connect one logic block with another. Okay, so you can it's basically like plugging Lego bricks. So you can build something with that. So what do we put in this FPGA? What do we build with it? We can build a processor with it. So you can configure it to behave like a processor. So inside running, there is a Milkymist system on chip. So it's a lot of hardware blocks connected to each other and controlling the video, display, the music, a lot of stuff. And among this big system, there is a CPU. There's a processor, which is a LatticeMico32. And that's the block I'm going to talk about in this presentation, because that's the block which will run NetBSD. So now let's talk about the CPU. A bit of introduction. So LatticeMico32 is a 32-bit CPU. It's RISC, which means that there are very few instructions, but by using those very few instructions, you can build complex programs. It's big endian. It has 6 stages. I will explain a bit more about this later. And it's pretty efficient. It has instruction and data cache, and it's using Wishbone, which is a bus on the chip that allows all those hardware blocks to communicate, and it's interesting because it's totally open source protocol. Why is it interesting, this CPU? Because it's small, so it doesn't take a lot of resources in the FPGA kind of Lego chip. It's portable, so you can easily make it work on different chips. And if it's pretty fast, it can work faster than 100 megahertz. And it actually works. That's nice. And it has a lot of software support. So you can have GCC, you can compile. You have binutils, you can assemble assembly. You have GDB for debugging. You have QEMU to emulate the hardware. So you can use your computer to run software as if it was running on the FPGA. And then it's open source, so you can read, learn from the design, modify, and share. OK, those are the good points. What are the bad points? Good, there is only one bad point. There is no memory management unit yet. And that's bad because with no memory management unit, I will explain later, but you can't run a modern operating system like Mac OS or Linux or NetBSD or Windows, because you need virtual memory and to make all the Unix process separation work. I'll explain a bit later, but you need this hardware block. So that's the first thing I've done, to add a memory management unit inside the CPU. So the CPU is used in closed source commercial chips. It's also used in open source projects like the Milkymist One. And as I said, it's pretty efficient because with some tests, we saw that it could achieve 800 megahertz on a modern chip process. Now let's have a look at the CPU pipeline. But first, what's a pipeline? So I'm quoting Wikipedia here, and computing a pipeline is a set of data processing elements connected in series where the output of one element is the input of the next one. OK, what does it mean? So you have boxes, which are data processing elements, and you can feed data in one of the boxes. It's processed, and then the result is outputted, and it becomes the input of the next box. So if you're a Unix programmer, you will understand this, and when you're doing a shell command with pipes that I put in red, you're basically building a pipeline, and the data processing elements here are the cat command, the grep command, and the word count command. So you have data flowing through this pipeline, and you get a result. So the bash history file is the input of cat, and then it goes to the input of grep, and then to the input of word count. So now back to the CPU. We know what a pipeline is, but what's a CPU pipeline? So here, as I said on the slide before, there are 6 stages. So 6 data processing elements. So that's the main machinery of the CPU. That's what makes the CPU work. The first box is address. So it's computing the address of the next instruction to fetch. Then, when you know the address, you're going to actually fetch the instruction. So that's the instruction fetch stage. And then, when you fetch this instruction from main memory, you're going to decode it because it's just raw 32 bits. You don't know what it means. You need to know if it's, for instance, an addition or a multiplication instruction or whatever. So you need to decode it. Then when it's decoded, you need to execute it. So if it's an addition, you're going to make the addition. And then, if the instruction was a memory load or store, you're going to access main memory and do the job. And then, when everything is done, the last stage is a register write back. It means that you're going to take the result of the instruction and put it in a register. Okay. Usually, we only put one letter for all these stages. So A for address, F for fetch, D for decode, etc. So how is it working in reality? I've put a little diagram. So for instance, at the first clock cycle, the first instruction is in the address stage. Then it goes forward and it's in the fetch stage. But in the meantime, the second instruction comes in the address stage because we don't want the stage to get idle. We want to use all the hardware blocks in our CPU at 100% to be efficient. And then, next stage, at the next clock cycle, the first instruction ends up in the decode stage, the second in the fetch stage, etc. And so it's moving forward through the pipeline like this. And when the pipeline is full, you can see one interesting thing is that there is always one instruction being executed. So at each clock cycle, there is one execution. So it's pretty efficient. So now, let's look at a bigger picture. That's a simplification of the CPU. So you can see the pipeline on the left. And then you can see that, for instance, instruction fetch stage needs to be fetching instructions. So it needs to be accessing main memory. But main memory usually is off-chip. It's outside the CPU chip. And access is pretty slow. There is a lot of latency, so access in main memory is slow. So we put a cache in between. So usually the instruction fetch is going through the instruction cache, which is on chip. It's in the CPU, and access time is pretty fast. It's just one cycle usually. So okay, that speeds things up. And same thing for the memory load and store. You're accessing main memory through data cache. But one thing important to notice here is the word physical address. It's written almost everywhere. Why? Because even if you're going through instruction and data cache, it's the address you're manipulating in the pipeline are the same addresses here that are going out of the CPU on the electrical lines and connected to main memory. There is no translation unit anywhere. It's just the same addresses. So we call them physical addresses because they are going out in electrical wires and directly indexing main memory. And that's not going to work. You can't run modern operating system like this. You can't run NetBSD, for instance, because to have your separate Unix processes, you need something called the virtual memory addressing, and you need each process to have the same memory layout and to be able, for instance, to have at the same virtual address different data. So you need two kind of level of memory. You need physical addresses and virtual addresses. So we're going to add something in this diagram, which is the memory management unit, and which is going to do the translation. So now, on the left, the pipeline is only manipulating virtual addresses. Why are they virtual? Because they never, ever end up to be accessing main memory. In fact, instead of this, you are going to do memory MMU lookup. So you're feeding the virtual address to the memory management unit. It's going to translate it into physical address. And then this physical address is going out to main memory. So that's the modification done to allow the CPU to run a modern operating system. So what's the MMU's, or memory management unit's, job? As I said, it's translating. It translates a virtual address to a physical address. Okay, it's not only doing this, it's also doing memory protection. It allows to either allow the CPU to read or write memory, but it can deny access. So with this header block, you can deny a write to a read-only address, for instance, or you can deny execution of a memory block. And it's useful to prevent software bugs or security issues. So now let's try to understand really how it works. So this is again simplified. You have the CPU pipeline on the left issuing a virtual address to the memory management unit, and the memory management unit is translating it and generating a physical address to index RAM. That's great, but how does the MMU know how to translate the virtual address to the physical address? How does it know? It's using the page table. The page table, as you can see with the curly brace, is located in main memory. So that's a data array located in main memory, which basically just contains the association of a virtual address to a physical address. Just data containing the association. It's maintained up to date by the operating system, and it's accessed by the memory management unit. Okay, why is it called a page table? Because it should be simple to call it, for instance, address translation table. Why page table? Because we're using pages, in fact. So the physical memory has been divided up into small regions called pages. Because we need a bigger granularity to keep the page table small. Let me explain why. Let's take an example. We want to translate addresses. So we want to, for instance, translate the address 4, and it will be the physical address 1 and all zeros. And for instance, address 5 would be address 1 and all zeros and 1s and 1, etc. You're noticing that here, I'm using 3 lines for 3 addresses. It's really not efficient at all. So I would need thousands of lines to translate just thousands of addresses, so thousands of bytes. It's really not efficient. It's wrong, it can't work like this. So what we're using instead, we're using pages. So we're instead translating chunks of memory. So there is a chunk of virtual address, which is 000, and then something. We don't care about the least significant bits, and we translate it to a physical block. And those chunks are the pages. The page is just a chunk of memory. So here, in 3 lines, so in just 3 entries of the page table, I mapped thousands of kilobytes, several kilobytes of memory instead of just 3 bytes. So it's more efficient and it keeps the page table small. So okay, we're talking about pages now. But there is something else that you need to notice here is I said previously that accessing main memory was pretty slow. And now I'm saying that every time you need to translate an address, you're accessing a page table in main memory. Isn't it going to slow the CPU down? In fact, yes, but we're not doing this. We're putting a cache in between. So, in fact, MMU doesn't access the page table directly. It's accessing a TLB. TLB stands for Translation Look-Aside Buffer. That's a clever word, but it's just a cache. It's a subset of the page table, and it's caching the virtual address to physical address translations. So, for instance, the first time you want to translate a page, the MMU will go to fetch in main memory in the page table in RAM, which is slow, but then the result is stored in the cache in the TLB. And then the next time it's going to be very fast. In 1 cycle, you will be able to translate an address. So TLB is really interesting here. And the TLB is a hardware block in the chip, in the CPU. It's not outside. So that's approximately how your modern CPU works, like your modern x86 or ARM device work. But in fact, here for LatticeMico32 CPU, I didn't do like this. In fact, the MMU, when the information is not in the TLB, will not go fetch by itself into main memory. In fact, when the information is not in the TLB, the MMU will raise an exception and it will trap into the operating system and ask the operating system to update the TLB. So it's going to be a bit slower, and then when there is no information in TLB, a bit of code will be executed to fetch in the page table and update the TLB. So we say the TLB here is entirely managed by software, not by hardware. Okay. Then, now that we know a bit how the MMU is going to work, let's talk about the features. The page size. This MMU only supports 4 kilobytes pages. So, one question now. So I've put a little bit physical address here. The X's are just for the 1 or 0 of the binary. How many bits of an address indicate the offset within a given page if we say that the page is 4 kilobytes? And heard something here? 12. Great. Okay. So you need 12 bits. Why? Because 2 to the power of 12 is 4096, which is exactly the size of 4 kilobytes. 4 kilobytes is 4096 bytes. So in an address, we can split it into 2 parts. One is the offset within a page, which is 12 bits long, and the other part is the page number, basically. So 20 bits for the page number. And that's going to be important for the following. So then, we talked about the TLB. In fact, there are 2 TLB, 2 translation look-aside buffer, one for instruction, the ITLB, and one for data, the DTLB. Each TLB here contains 1,024 entries. So how many bits needed to index the TLB? How many? Almost. 10. Okay, because 2 to the power of 10 is 1,024. Almost. So, you only index 1 TLB. Okay, I got it, okay. When you index 1 TLB, it has 1,024. It's 10 bits. Okay, got it. So 10 bits. And then, as I said, there is no hardware page tree worker. So, I mean, there is no hardware block designed to automatically fetch from the page table when it's missing from the TLB. So it's doing in software. It's software assisted. So, okay, we've got a hardware block called MMU. We're feeding it a virtual address. We're feeding it if it's a load or a store, and if it's instruction data, and it's producing a physical address, and it's saying if the access is granted or denied. But it's not just that, because, in fact, the MMU needs to be able to say something else. It needs to be able to say, I don't know. Because, as I said, the TLB is software assisted, so sometimes the MMU can't know because information is not in the TLB. And so when the MMU says, I don't know, it's raising an exception, and it goes into the operating system to know, to search for the translation and update the TLB. So now, let's have a look inside the TLB. Let's try to understand how the TLB cache works. So we're going to take an example here. We're going to try to translate one address to see how it works. So let's take a virtual address I've put on the top of the slide, 0xA0001004. So, as I said before, we can split the address into 2 parts. The offset in the page, which is 4, and the page number. For now, we're going to put aside the offset in the page, because since we are only translating pages, we don't care about the offset. The offset will not be translated. We will only translate the page number. So put page offset aside. So now we have a virtual page number, which is the left part of the virtual address. Let's translate it to binary. So it's just a sequence of 1 and 0. And now we are going to index our TLB with this page number. So as we said before, we can only index the TLB with 10 bits. because there are 1,024 entries. I've only written 3 lines here, but keep in mind there are 1,024. So we are choosing, just like this, the 10 lowest bits of the page number to index our TLB. So this is going to choose the line that we're interested about. So it's going to be the line number 1, so the line in the middle. OK, so now we can read the content of the line now that we've indexed it. So on the right, we see that there is a bit that says if the line is valid or not. That's a valid bit. It's 1, so it's OK. The line is valid. We can keep on reading. There is a bit that says that the page is read-only. So the MMU knows that if we are trying to do a store, for instance, if we're writing, it's going to be denied. So it's only allowed to read. OK? But then we want to translate. So we have the physical page number field. That could be our translation. Why could? Because, in fact, if you look at the binary representation of the address, we've only taken the 10 lowest bits to index and to choose the line. So we could modify any of the bits. The first bits here, the 10100, we could modify any of these, and it would still have selected the same exact line here. So we have actually 1,024 addresses here that could change and which are fighting for the same line here. So how can we be sure that we are indeed reading the information we are looking for, that we are reading the translation of this address and not one of the others which are fighting for this line? That's going to be inside the tag information. This here is going to give us this information. So we're going to do a tag check. So we take the 0x280 information, we translate it into binary, and we compare it. We compare those two values. We compare the 10 upper bits. And if it's equal, it means that the tag check is a hit, and then it's really the information we're looking for. So it's OK. We're reading the good line. It contains information. Information is valid. So we can take for granted that this here is the translation we're looking for. So we have the physical page number now. It's B0001. But it's not an address yet. We need to append the page offset. So as I said, it's not translated. So we just append the 4, which was here and here. We append it in the end. So now we have the complete physical address. And we've translated an address. Great. TLB is working. So now it's over for the hardware part. Let's talk a bit about how to port NetBSD and how to modify the software to allow it to run on this new CPU with an MMU. What's cool about NetBSD is that it always uses cross-compilation toolchain. So you don't have to worry about going on the internet, on the web, and searching for a toolchain to download GCC, try to compile it, fail, and try to patch it, and try to grab binutils. No. You just run the script on the bottom of the slide, which is inside a repository of NetBSD. It's called build.sh. And it will generate for you the good toolchain, the good cross-compilation toolchain. So you can be in Ubuntu, macOS, whatever. It will generate a toolchain that works on your system and that targets your CPU architecture. So that's great. So you need to modify a bit the build.sh script to make it understand your new architecture, to modify makefile here and there, to know about your new architecture, and then it will generate a toolchain. Now that it's done, one thing that made me lose a bit of time, so I'm telling to you, is that NetBSD kernel is not linked against libgcc. What does it mean? First, you need to know that when you're compiling a normal C file, usually GCC when it sees a multiplication or division or shift or something like that, it will not directly emit assembly code for this multiplication or this division, etc. Instead, it will put a function call to the multiplication function. And then, at the linking stage, it will link with something called libgcc, which contains those functions for multiplication, division, etc. But since NetBSD is not linked against libgcc, we won't have those. So we need to put them in libkern, because the kernel is linked against libkern. So that's a trap to avoid. So you want to put those division and multiplication, shift, modulus, etc. arithmetic functions inside libkern in syslib libkern architecture. Okay, then we want to build our kernel. So we're creating a directory for our architecture, which is LM32, and for our system on chip, which is Milkymist. Then we populate, so you put your include files that you can copy at first from other architectures, and then you modify them a bit to adapt them to the new architecture. Then in the configuration directory, you put the kernel configuration, which just selects what goes in and what's not going in. And then you stub. What I mean by this is that you're going to write code, but you don't want to just write code. You want to test it. So if you're implementing functions right now directly, you will not be able to test them, because at first, until you got everything written down, it wouldn't compile. So what you want to do is first take every function you need to write and just write empty functions, just stubs. Because then you will be able to compile your kernel and get a binary image that you can run, and then you can begin to implement, because then you can test, then you can debug. So the command in the bottom of the slide is a pretty simple command that will build a kernel using generic configuration for the Milkymist architecture. Another thing that you want to do usually when you write kernel code is you want to be able to debug your code, and you want to be able to print stuff. So one first thing to do is to write the console driver to be able to print stuff. It's pretty straightforward here to do. You just have to declare one C structure which contains function pointers, and one pointer is for the getC function, which reads from the console, and one is the putC function, which writes to the console. Then once you've written this, you will use it later. So a bit of how the basic kernel boots. First, when it boots, it goes through the exception handler, so it goes through the reset handler, and you need to put a bit of assembly code to initialize the CPU and to clear BSS, for instance, but then you want to quickly get out of assembly code, because assembly is a nightmare to read, to debug. You want to go to C code. So quickly you will call a C function, for instance, Milkymist startup, and you will do the rest of initializing from a C code. So first, as I said, you want to debug, so you want to initialize the console driver. You do this by calling consinit, which will call the Milkymist attach a callback for the driver, for the console driver. And then, an important point here is to assign the pointer of the structure you've written previously, this structure, you assign it to the cntab symbol. And this is the symbol which is dereferenced by the NetBSD kernel for each print. So when you do this assignment, you can print. You're OK. Then you want to initialize the memory subsystem, which is called pmap in NetBSD. So you call the MD function pmap bootstrap. What is MD? MD is machine dependent. It means it's low-level code that is tightly coupled to your architecture. It depends on the low-level parameter of your architecture. So it means every MD functions, you are going to write them, because you need to rewrite them for each architecture. So you will call this pmap bootstrap, which will initialize memory subsystem. Then, when it's done, you can let the kernel boot. So you will call the main function, and the main function is machine independent, which means it's already written for you. is just a main function of NetBSD kernel. It will boot every subsystem of the kernel. Okay, so we're calling pmap bootstrap, but we need to implement it. So we need to implement the pmap subsystem. Pmap is a machine-dependent portion of the virtual memory system. So okay, you need to implement this. You need to, for instance, fetch the amount of physical memory that your system have, register it inside the system. You need to set up the page table of the kernel, do a few things like this. But then it's not all. You need to implement a few other callbacks, pmap init, pmap create, etc. But in fact, I was kind of lucky because since we have a software-managed TLB, there is already a piece of generic code sitting in sys UVM pmap, which already handles the software-managed TLB. So in fact, I didn't even have to write this code. I just took it. It was already existing. It works for PowerPC Bookie, for instance. So great. Let's work. Then we need to implement copy in and copy out, which are basically functions which copy data from process virtual address, from virtual process memory to kernel memory, and the other way around. So it's mostly used during system calls. Then we want to implement atomic operations. Atomic operations are used when you want to access, read, and update a variable, a memory location, but you don't want, in the same time, another thread to modify it. So you want the operation read, modify to be atomic. The problem here is that there is no atomic instruction in the LatticeMico32 CPU. So to handle this, we used restartable atomic sequence and to implement a very basic piece of atomic operation, which is compare and swap. When you use compare and swap, you can then build all the other atomic operation from this. You can build mutexes and spin locks and everything. So what is a restartable atomic sequence? Basically, the principle is, so that's the entire implementation of the compare and swap in LatticeMico32. So you can see there are 5 instructions: 1 load, 1 branch, 1 store, 1 move, and 1 return. So it's not atomic at all, which means that in the middle of this function, there could be an interruption, and the CPU could go do something else, and then want to return. So that's bad, that's not atomic. So to work around this, there is a symbol here, which is ras start, which is defined, and then at the end of the operation, there is a ras end. And the trick here is that when the CPU is interrupted, goes doing something else, and wants to return, here, it will check to see if it's going to return between a start and end tag. And if it's the case, then instead of resuming where it was, so for instance, instead of resuming here in the branch not equal, it will resume at the start. So it's a restartable atomic sequence. So that's the trick to make it work. Then, when you have the atomic operation, you can add support for interrupts. So basically, the idea is to allow the device drivers to register interrupt callbacks, interrupt handlers. So you can do this. Then you want to have a system clock running. What the system clock is really important because that's the event that will trigger the update of the system time of your system. It's also the event that will make the CPU schedule between processes and switch from one task to another and schedule things like soft clock interrupts. So what you need to do is to write the CPU init clocks. It's another machine-dependent function you need to write. And this needs to be doing basically the clock driver initialization, set up a timer, set it at restartable, start the timer, and register the interrupt callback so that when there is a timer tick, it will call your callback function. And then you need to write the clock interrupt handler that is going to be called when there is a tick. And this handler needs to call the hard clock. That's the machine-independent code that will increment the time of the day and run the virtual and profiling time accounting for processes and schedule software interruption, etc. Then you have a bunch of other functions to implement that all are machine-dependent. So for instance, you want to implement a function that allows to switch from one context to another. It's called CPU switch to. And then you want to allow to copy data and stop on page fault. Then you want to allow to save context. And you want to write the low-level part of the code, which is finishing the fork operations. All of these needs to be written for each architecture. Then you have tons of functions to write, basically. Those are just a few examples. OK, so when you've implemented all those functions, and you can build your kernel, you can test it, you can run it, you can fix it, but it's only the kernel. You're still just booting the kernel, and you need to worry about the user space now. To try to boot and to debug user space, you need at least a root file system, which contains files. Then you need to create a dummy file system. You put inside an init program, which is basically the first ever program to be run by your system. And you build your kernel with MFS support. MFS stands for Memory File System, so to support the file system embedded inside the kernel. And then you insert your root file system inside the kernel image using the MD setImage script provided with NetBSD. Yeah, then you can try to boot it. So far, in my porting to NetBSD, I only have the kernel to boot. So far, the user space doesn't boot yet. So let's have a little demo time. Let's hope it works. OK, first bug. OK. So let's pretend I'm doing a modification in the code. So I'm going to just touch a file. OK. Then I want to recompile. OK. I will use the build.sh script. I say it's architecture Milkymist. I say I am not root. And that I just want to rebuild what has changed, not everything, because we don't have the time. Then I say I want to select the generic configuration for the kernel. Then I hit Enter. And it will cross-compile my kernel. It's done. OK, we've built a kernel, and it's located here. So now we'll try to run it. So it will be too long to demo on the board, so I'm going to demo on QEMU, which is an emulator emulating the entire system on chip running usually on the FPGA. So let's try to run it using QEMU. OK. So there is QEMU. We say we want to emulate the Milkymist system on chip. Then we select the CPU. It's LM32 with full divider and multipliers, and with MMU. Then we say we don't run any graphics, and we select the kernel. The kernel is here. Then we run. OK. So it's going through a bit of stuff, and then it ends up by wanting to load a root device and wants to... OK, it splits. OK, sorry. OK, it ends up wanting to load a root device to load a root file system, but since I didn't put any file system inside the kernel, it cannot find it. So far, I can only type halt or reboot, and that's it. So let's walk through a bit inside this. So at first, it's the low-level initialization. It's trying to account for the physical memory which is present. Then it's calling the pmap bootstrap function. It's initializing the virtual memory subsystem. And then it's calling main. And main function is basically initializing every system inside NetBSD. So you can see all those init prints here. It's the main function initializing everything. And then, when it's done initializing, it will try to initialize the device drivers. Here there is a timer, which is initialized, then the console driver, and then the clock, which is ticking to maintain the system time. Then it's turning interrupts on to allow the clock to tick, and then it's trying to mount the root file system. Okay. Thank you. And I want to thank all the people that made this project, the MMU part and the porting part, possible. Sebastian, Michael Valle, and all the people who helped a lot in this. This is in no particular order. So thank you, everyone. Thank you for listening. And if you have any questions.
Any questions?
Okay, first, thank you for this excellent talk. And I have two questions, in fact. The first one, you say that if a TLB entry is missing, then it has to jump into the kernel and resolve the page table entry.
Right.
But if there is no TLB entry for the code in the kernel is going to execute, how does this work? It's a bit of chicken and egg problem.
I'm sorry, can you repeat the end of the question? If there is no TLB entry?
If there is no TLB entry for the code in the kernel that it attempts to execute, the handler for the missing TLB entry.
Very good question. Okay, in fact, it's clear that if there is no TLB entry, for instance, for the kernel code, it's a chicken and egg problem. But when there is an exception, we disable the MMU. So the exception handlers are running using physical addresses only. So we disable the MMU, the address translation. We fetch from the page table, we update the TLB, and then we enable back the MMU and we restart the operation.
I see. And the second question. So you show that the compare and swap operation works by comparing the addresses and jumping to the start of the operation after exiting the interrupt somehow. But how is it done? Does the CPU just have two registers with addresses of compare and swap?
No, it's just done in software, actually. So it's just in the return path from interrupt. When you get an interrupt, you save the context on the stack somewhere. So you save all the registers and you save the PC. And when you want to go back, you just do a little test on the PC value.
So
If PC is superior of start or n inferior of n, then we need to do a special case and we do PC equals start. So it's just in software.
So you cannot have that in user space code.
No, it's handled in the kernel code, in the return path from interrupts. That's a very good question, but since we are only using one function to build all the atomic operations, which is comparison, so there is only one location, so only one.
So would the user space need to call into the kernel to make a compare and swap operation?
So far, it's only for the kernel when it's doing atomic operation. What I said is only working for the kernel, indeed. For user space, I didn't thought about it yet. There is no user space working yet. But to have atomic operation inside the user space, I think I would need some kind of system core. I don't know, maybe like Futex for Linux. I don't know.
Okay, thank you.
Thank you.
Hi. I had a question about the interaction between the caches and the TLB. Usually there is this debate if you are virtually indexed, physically tagged. I wanted to know what you chose for these classes of CPUs.
Okay, really good question. Indeed, if you want to have an efficient design, you want that the MMU lookup. Oh, there is no slide. Can we put the slide back? Is it possible? Okay, thank you. If we want not to lose time here, we want both the MMU lookup here and the cache lookup to be simultaneous, because we don't want to lose time in this path. So to allow it, we need to index the MMU indeed with what we have, the virtual address here. And then we also have to index the cache with the virtual address. So both are virtually indexed. But then, indeed, in the caches, if you want to be able to tell if the data cached corresponds to what you're looking for, you need to tag using the physical address. So here it's VIPT, virtually indexed, physically tagged. Here it's VIVT, virtually indexed, virtually tagged, to allow for simultaneous lookup and not lose time and be efficient. Does it answer your question? Okay.
Other questions?
It's actually more for FPGA. You use Spartan 6 FPGA,
Yeah.
but why didn't you use like microblaze processor, but some other vendor processors?
You mean why did I use LatticeMico32 instead of microblaze?
Yes.
I'm not sure microblaze is open source, is it?
I think
I'm not sure it's open source, and it's definitely not free software, I guess. There is a restricted license.
okay, then I understand.
Yeah. There's a question. I just will answer after, but just a question here.
Yeah, I just wanted to ask, right now you're running in QEMU, but once you have a user space, I guess you'll want to run it on the FPGA. When you do that, how many of those programmable logic blocks do you need to implement the MMU compared to some of the other parts of the CPU? And then the other thing I'm wondering is, when you're developing this code, how can you possibly test it
You mean
when it doesn't come all the way up? The kernel doesn't come all the way up. What do you do to figure out what's wrong?
well, to fix kernel bugs? Yeah. Okay. Okay, there are several questions. The first one, I don't have precise numbers about the size that the MMU adds, but in terms of logic blocks, it's not much. It's really not big. It ends up being a bit bloated because you have TLBs, which are big, 1,024 lines, but it's mostly using RAM blocks in the FPGA, which usually are not used anyway. So it's space you lose usually, so you don't mind using them. So and it's logic is not big. And on the other question, to debug kernel, what's really awesome to debug the kernel is QEMU. Because when you run your kernel inside QEMU, you have a GDB debugger server inside QEMU. So you can attach GDB client to QEMU, and I'm using this all the time. And you can basically put breakpoints and inspect memory, and you can do whatever you want. It's just the couple GDB and QEMU is awesome for kernel debugging. I think that there was a question here.
Question here.
With a mic.
I don't think that you can answer this question because
Try.
it's not you that designed the Milkymist, and the specific core Lattice Micro was chosen by Sebastian, I think.
Yes, indeed, yeah.
So this is to answer the question of Mr. So the architecture of the CPU was fixed.
The CPU was already chosen. I didn't choose it, indeed.
But just for information, there are also plenty other open source CPU projects.
There are a lot of open source CPU projects. It's kind of
Like,
growing up here and there. Most of them are not really efficient. And but there is one really good open source CPU, which is OpenRISC, which have a talk tomorrow, I guess. So Julius Baxter tomorrow will talk about it. And
okay,
but there is not much good open source CPU.
Speaking about OpenRISC, you think that compared to Lattice CPU, it's a good competitor?
Yes, definitely. It's really good. It's totally open source. If I had to name a wrong point about OpenRISC, it would be that it's a bit bloated. So it's using a lot of FPGA resources compared to LatticeMico32. But it's really great. It's really efficient, and it has a lot of software support, especially the toolchain. The community is actively working on it, and so far it has an MMU which is working really well, and it's already booting Linux, kernel, user space, everything. They are even running X and running old school games in ScumVM and etc. So it's really a nice project working really well.
Speaking about resources on the FPGA, the Lattice CPU, how many slices did it occupies?
I really don't have the numbers, but inside a Spartan 6, which is not so big, I don't know. It's using. Maybe ask Sebastian. He will know.
Okay. And if you speak in percentage,
I really don't remember, but it's really not using much.
No,
you can even put several.
I'm speaking about your implementation of the MMU. By which percent, or how many percent it increases the occupation of the FPGA?
I didn't compute it, but what I can say is that by adding the MMU, it's definitely not increasing what we call the critical path in the logical design. So it's not reducing the frequency of the CPU.
Okay.
So you get the same performance by adding the MMU. In terms of numbers, I don't have them, sorry.
No problem.
And this middle step of having the MMU in software, is it a middle step, as I'm saying, and you will go to a hardware fetch, or is it going to stay like that? And if it stays like that, do you have an idea of the performance hit?
The reason usually to use a software-managed TLB instead of a hardware one, usually it's just laziness and simplicity. So it was one of my first digital design try, so I wanted to follow the KISS rule, keep it simple, stupid. So I just did the easiest thing to do, so software managed. But there is no reason to not use hardware managed. It's really more efficient. It's better to use hardware managed TLB. And about OpenRISC, their MMU is hardware managed, so it's more efficient definitely than what I did here. So maybe if I have time and motivation in the future, maybe it will end up being hardware TLB.
So at least if you could make it a two-way, that could help.
What do you mean two-way?
Because I don't know if you have ways in your TLB.
In TLB, no, I don't have ways.
Okay.
Only in the caches.
Okay, thanks.
Time for one more quick question, I think. Anybody? Cool. Thanks for that really great talk.
Thank you.